Hello again. And now we're going to talk about buffers. Okay, so let's just take a deep breath. Okay, we're going to go over the stuff we did in class first, and then we're just going to finish this section on buffers. All right, so we talked about this in class, and I showed you the demo. Buffers resist change in pH when you add a strong acid or a strong base. Okay, so that's the whole point of a buffer, is to keep things even. Keep them from changing pH. So the way you make a buffer is it has to contain a combo of a weak acid and its conjugate base, or a weak base and its conjugate acid. Now the easiest way to make this is to take a weak acid, like HF from the previous example, and add in the salt of the conjugate base, like sodium fluoride, okay? Because now you have a solution that contains HF, the weak acid, and F minus, the conjugate base. Another really easy way to do this is take ammonia, NH3, which is a weak base, and add ammonium chloride. So NH4 plus is the conjugate acid of the weak base. Okay, so it can't be a buffer if you have a strong acid and a strong base. That doesn't work. It has to be a weak acid and the conjugate base, or a weak base and the conjugate acid. Okay, and it has to have both. Both parts, otherwise it doesn't work. Okay, here's our example we did in class. All right, so if we have a buffer solution, we have 0.5 molar acetic acid and 0.5 molar sodium acetate. We have a buffer. Ta-da! We have a buffer because we have weak acid, conjugate base. We want to know the pH. All right, so the important species in this case is the undissociated acid, HA, HCA2, H3O2, and H plus, and the conjugate base, which is the acetate ion itself, C2H3O2 minus. All right, now in a buffer, we have initial concentration of both parts. So we're going to put that in our ice chart. Now, because we have a 0 for the H plus, we're going to have plus X minus X minus X, okay? Because the equilibrium is going to shift to the direction. So if there's a 0 in the chart, it's going to shift in that direction, okay? Now, because of our approximation, our equilibrium concentrations are 0.5 for the acid, X for the H plus, and 0.5 for the conjugate base. So when we write our equilibrium expression, and we plug in what we know, it's just like the previous example, all right? Our hydrogen ion concentration is going to be equal to the Ka value. That's because the concentration of the acid and the weak base are equal. Okay, so when we want to find the pH of that solution, we take the negative log of the Ka. Okay, and guess what? That's called the pKa. Okay, so a buffer that has equal amounts of acid and conjugate base, the pH is going to be equal to the pKa of the buffer system. All right. Oh, there's the answer. 4.74. Now, we can also use the Henderson-Hasselbalch equation. So pH equals pKa plus the log of negative A, which is the conjugate base, over HA. So the concentration of A over the concentration of HA. All right, so if we plug in what we know, we take the pKa of negative log of 1.8 times 10 to the negative 5. The log of 0.5 over 0.5 is 0 because the log of 1 is 0. There we go. pH equals pKa if those two concentrations are equal. Henderson-Hasselbalch equation is on the equation sheet. Okay, now here's where it gets complicated. Okay, when we add an acid or base to our buffer system, it's going to change the amount of acid and conjugate base. Okay, so what happens is if you add an acid or base, we have to do two steps here, because we have to do a stoichiometry calculation first, because we have our strong acid or strong base is going to react in a one direction reaction with part of our buffer system. If you're adding acid, it's going to react with the conjugate base part of the buffer. If you're adding a base, it's going to react with the acid part of the buffer. Remember, we're adding a strong acid or a strong base. So if we add a strong acid, we're adding H+ ions. If we're adding a strong base, we're adding OH- ions, okay? So we're going to do 2 steps here, not 3, 2. We're going to do what I call a BAC chart, which is BCA, before, change, after. That's our stoichiometry. And we're going to take those after amounts, and that'll be our initial concentration in our ice chart. Okay, so let's try it. All right, so here's our problem. We're going to calculate the pH change that occurs when we add 0.1 molar NaOH to a 1 liter of a buffered solution from the previous example. Oh, isn't that nice? We get to use what we know from before. Okay, so we have 0.5 molar acetic acid and 0.5 molar sodium acetate. Now, NaOH is a strong base. Okay, so we're going to be adding a strong base. So the OH- ions are going to react with our conjugate, our weak acid. Okay, so here's our BCA chart. C or reacts. Before reaction, the change in reaction, after. Okay, so before anything happens, we have 0.5 molar of our weak acid, and we're adding 0.01 moles of OH-. Okay, now for this part of the reaction, we're going to do it in terms of moles and not molarity because it's a limiting reactant problem. Okay, are you with me? And then we already have 0.5 moles of the conjugate base from the buffer system. So remember, the buffer is the acid conjugate base, and they're equal, but we're adding a strong base. So what's going to happen is the OH- is going to react, and it's going to be completely used up. And it's going to react, the amount that it's going to react is going to be 0.01. And so therefore, because it's all a 1-to-1 mole ratio, our weak acid is also going to go down by 0.01. And our weak base, our conjugate base, is going to go up by 0.01. So after this one-directional non-equilibrium reaction happens between the weak acid and the OH- ions, what's left is 0.549 moles of the weak acid and 0.51 moles of the conjugate base. So notice what's happened here. We have made a slight shift in our amounts of our buffer system. Okay, so we kind of took it, it was equal, now it's, okay. So now we can use our Henderson-Hasselbalch equation. We don't have to make an ice chart here. Our after reaction concentrations and molarity is going to go right into the Henderson-Hasselbalch, okay? Oh, well, I'll show you what it looks like with the ice chart first, and then we'll do Henderson-Hasselbalch, okay? 0.5, 0.49, 0.51, and 0. Okay, so we have our initial concentrations, minus x plus x plus x. Okay, we can use our approximation because the amount of dissociation is going to be very, very small. All right, plug it into our equilibrium expression, and here we have, we're going to solve for x. Okay, so we just need to crank out the algebra here and solve for x. The pH is the negative log of x. Notice that it's gone up just a little bit. Not that much. It has changed a little bit. It's become a little bit more basic. So, which makes sense because we added a strong base to the system. So by adding a strong base to a buffer, we are making the pH go up a little, but not dramatically. Not like if it was not a buffer. Okay. So we've increased the pH by 0.02. So yes, it has gone up a little bit, but not that much. Okay, now here's what it would look like with Henderson-Hasselbalch. This is my preferred method because it's just streamlined, okay? What I like to do is calculate the pKa ahead of time and just stick that in there, okay? And then we're going to put into our equation the after amounts of the conjugate base on top and the weak acid on bottom. Now, in the case of this equation, we did it in terms of moles, but because they're all in the same solution, they have the same volume. So you don't have to make it back into molarity if you don't want to, okay? Because the volume cancels out. If you do, it's not going to change the answer. You'll get the same answer. Okay. Everybody with me so far? All right. Let's take another look. Oh, that was our example on page 3. Okay, let's do another example. Now we're going to take the system and we're going to compare this to the pH change if you were to add 0.1 molar of NaOH in pure water. Okay, now in this case, this is what we did in class where we added 5 drops and then pH went crazy. If we add 0.5 moles of NaOH to 1 liter of water, what happens here is we get complete dissociation of Na plus and OH minus. So now we have 0.01 molar OH minus in the solution. Okay. So pOH of negative 0.01 is 14, is 2. 14 minus 2 is 12. So without the buffer system, and we add that same quantity of OH, the pH goes to 12. Okay, so it does work. All right, now we're going to do the same thing, but this time we're going to use the same system and we're going to add acid to it. Okay, now in this case, when you're adding an acid to your buffer system, the H plus is going to react with your conjugate base in our one-way street, in our one-way reaction, okay? So what happens first is this should not be an equilibrium. Oh, here, right here. That's a one-way street. So that should be a one-way arrow, not a yields reversibly. Okay, sorry about that. Okay, so we start with 0.5 moles of the acetic acid, the acetate ion, 0.5 moles of the acetic acid, and we're adding H+. It's going to react with the H+. So all of the H+ gets consumed. Only 0.02, the same amount. It's all 1-to-1 mole ratio. So we're going to go down by 0.02, down by 0.02, and then we're going to go up by 0.02. So after this one-way street reaction is gone to completion and done, what's left over is now we've adjusted our quantities again. We made a little, our conjugate base has gone down by 0.02 and our conjugate acid has gone up by 0.02, okay? So now when we plug it into Henderson-Hasselbalch, pH equals pKa plus the log of A minus over HA. We have 0.48 over 0.52. Our pH is slightly lower. Okay, that makes sense because we added a strong acid. The pH is going to go down a little bit, but it's a buffer system, so it's not going to go like kabamo. Okay? Now, where are we here? Weak base buffers. What's this? Ah, right. If we have a weak base, we have, ammonia is our favorite weak base. It's really the one we see all the time. The Kb for our base is 1.8 times 10 to the negative 5. And so we have a buffer system. Ooh, it's not equal. Okay, that's okay. Let's not panic. We have 0.25 moles of ammonia, a molar, and 0.4 molar of NH4Cl. Okay, here's our equilibrium system. We have NH3, yields reversibly, NH4 plus OH minus. Don't forget, we're adding a water in there, okay, in order to make it all work out. So NH3 is acting as a base. Here's our initial conditions. Minus x, like normal. When we solve for x this time, it's going to give us our pOH. Okay, here's our equilibrium expression. This is a weak base system, so you're going to use Kb is equal to NH4 plus, which is our conjugate acid, times OH minus over the NH3. Plug it all in, and we solve for x, which is our OH concentration. pOH is the negative log of x. So we get pOH subtracted from 14, and ta-da, we have our pH. And no surprise here, the pH is in the basic range, okay, because ammonia is a weak base. All right, Now, we can also, I don't really, this version is not on the equation sheet. So, okay, so if you want to try to memorize this, you can. I like to teach kids to use the original form. But this is what it looks like for a weak base, okay? And this might be a little less confusing if you have a base system. The POH, it looks almost identical to the original one. It's just that we have POH equals PKB, which is the negative log of the KB, plus the log of the conjugate acid over the weak base. All right, so it's really similar to the other one. It's just that we've written it in terms of the base instead of the acid. Okay, so for our problem that we just completed, we would do the pKb of the weak base system, which is 4.74, and then the log of the conjugate acid over the weak base, and that would give us our answer as well, 9.06. Okay. We're almost to the end of this section. Hang on. Okay. We're just going to try to give you a little summary, all right? So, buffer solutions, they contain a significant quantity of acid, conjugate base, base, conjugate acid for a weak acid or weak base system, okay? When you add H plus to a buffer system, it reacts with the conjugate acid. When you add H plus to a buffer system, it's going to react with, sorry. When you add H plus, it reacts with the conjugate base. If you have a weak base buffer system, it acts with the weak base, okay? Acid reacts with base. When you add a strong base, it's going to react with the acid, okay? So if you have a buffer system made out of a weak acid, the strong acid is going to react with the weak acid. The strong base is going to react with the weak acid. Or if you have a buffer system where you're starting with a weak base, the strong base is going to react with the conjugate base. I shouldn't try to talk, just read. Okay. The ratio of those two things is what determines the pH of the buffer system, okay? So the buffer works as long as you have a significant amount of the acid conjugate base combo, okay? So if you put in too much strong acid or strong base, at some point you're going to use it all up, and you'll reach the maximum buffer capacity, and the buffer doesn't work anymore. Okay. Boom. That's the end of section 15.2. We're going to stop there.